Good afternoon, everyone, and welcome to Personal's technical webinar series. I'm your host, Jessica Bennett. Today, we're very fortunate to have Dr. Jeffrey Evans with us, presenting on the state of the practice for vertical barriers for control of contaminant transport in the subsurface. So during the presentation, we will keep all phone lines muted to limit any background noise. If you have questions, you can enter them into the chat at any time, or you can hold it till the end during the Q&A session, and you can either ask it live by raising your hand, or you can enter it in the chat and we will read it out to answer it. This webinar has been approved for 1 PDH credit. If you'd like to receive a certificate for that, you will need to download the attendance form. I will post a link to that form momentarily, and again later in the webinar. Please go to that link, look at the form, and download it. There are 4 multiple choice questions you will need to answer in order to receive credit. And if you have any issues accessing the form or getting to the link, just let us know and we can get that to you after the webinar. And finally, this webinar is being recorded and will be posted on our YouTube channel in the next few days. Next slide, please. So I'll briefly introduce Dr. Evans. He will give a core value moment to start off, followed by his technical presentation, and then we will have a Q&A session at the end. Dr. Evans is one of the world's leading experts on barrier wall technologies. He has over 70 papers published to date on the topic, and he's also a co-author on 2 books. He has over 50 years of total experience, including being in the U.S. Army Corps of Engineers. And he's a consultant for slurry wall projects in 15 states and 2 Canadian provinces. He's also a professor emeritus at Bucknell University. It's a great honor to have Dr. Evans with us today. And with that, I'll turn it over to Dr. Evans for the core value moment.
I just first say thank you all for attending, and hopefully whether you have little or a lot of experience with vertical barriers and slurry walls, you'll get a fair bit out of this presentation. And so with that, I'll get right to it. So you're all well aware of the 6 core values of Parsons Engineering: safety, quality, integrity, diversity, and innovation, and sustainability. For this talk, if I can get this thing moving, where are we here? I'd like to really touch upon 3 of these. Sustainability. As it turns out, passive containment systems provide perhaps the most sustainable remediation alternative, particularly for large, highly contaminated sites. We'll touch upon innovation. There have been a lot of developments recently, innovative construction methods and developments in our understanding of the performance. And to stay on top of these, we'll address some of the newer developments and our better understanding so that we have an improved ability to design and build vertical barriers. And lastly, quality. The quality of the vertical barrier to control contaminant migration really depends upon the attention to details in both the design and the attention to quality control details during construction. So with that, gone the wrong way here. We really have 4 parts to the presentation there we go. 4 parts to the presentation. We'll talk about deployment in environmental containment applications. We'll talk about construction methods that are available to you. Talk about, once we have those overviews, the second half of the presentation, we'll talk about soil bentonite slurry wall performance, since soil bentonite walls are the most common. And then we'll talk about cement bentonite performance, as they're probably the next most common. All right, so for deployment for environmental applications, we really have 3 different ways, and then there's an overlying decision in item 4: circumferential, upgradient, downgradient, and whether they're keyed in or hanging. And so the first slide shows the first 2 of these methods. By far the most common is shown on the left, where we have in the upper half of the drawing a plan view. On the lower half of the drawing, we have a section view, and a circumferential wall essentially surrounds the whole site. You can see in this cartoon, we have groundwater flow coming in from the left. We have the wall completely around the contaminated zone, and then we have groundwater extraction wells. And what you see in the cross section is the basically a hydraulic control system where the gradient is reversed. The contaminants are within the containment system, and groundwater at a low rate would be flowing into the system. And initially there'd be transient flow to pump down the groundwater inside, and then later steady state flow. I'll add that virtually all these control systems use some sort of a cap. It's pretty unusual to have a system that has no cap. On the right of this same slide is an upgradient barrier configuration. And similar, the groundwater is shown coming in from the left. And the wells are just down gradient. And if you look down below at the cross section, that really illustrates what's going on here. That is, a barrier only on one side prevents clean groundwater from encountering the contaminated zone and becoming contaminated. The groundwater extraction system reverses the gradient as far as the up gradient side is concerned, but it captures the down gradient plume. And in many cases, if the wall is built as circumferential, as in the left side, you cut off that plume, and then you have to have a whole separate remedial system to deal with the plume in addition to the contaminated zone. And by having an upgradient wall, you can deal with both the plume and the contaminated zone with the same system. So in the other method of the last, if you will, configuration is down gradient. And this is less common. I think Rocky Mountain Arsenal use this, where you want to use the groundwater to flush the contaminated zone. Perhaps the contaminants are at a low level. You don't really want to pump a lot of groundwater from the down gradient area into the system. So the vertical barrier is put between the contaminated zone and the down gradient water, and then you pump and you use the groundwater to flush it. That's probably the least common deployment. And then lastly, in all three of these methods, you have to decide whether the wall is going to be keyed in or touching some sort of aquitard, as in the upper part of the drawing, or is it going to be hanging, such as in the lower. So one of the common uses of a hanging vertical barrier would be for floating product. Another very common use is where there is no aquitard within a feasible distance. And in that case, you use hydraulic system, gradients, and you can still control the flow with a hanging barrier. All right, so the primary functions of vertical barriers for geoenvironmental applications are to reduce the off-site contaminant transport. That one's fairly obvious, but it's also to reduce seepage into the area as well as out of the area. I will, as I said, in virtually all cases, vertical barriers are used in conjunction with some low permeability cover system and some inboard pumping, and they're effectively a component in a hydraulic control system. I will add that all these technologies can be used in addition to containment to add strength for landfill stability. In that case, they're normally built perpendicular to the slope, and then those are called shear walls. And then they can be actually permeable walls for flow control with collection trenches rather than wells, or as a method to install a PRB treatment media. All right, so let's talk about the four methods more than four, the methods by which we can build a wall. We group those into four categories. We talk about continuous slurry trenching, and that's excavation is normally done with a backhoe or a clamshell. We think about another panel slurry trench method, And that's done likewise with a clamshell or some other specialized. Hydromill is one name, hydrophrase is another name. In addition to slurry trenching for vertical barriers, we can do in situ mixing. We can do in situ mixing with augers. We can do in situ mixing with chain mixers, jet grouting, and we'll talk about these as a comparison to slurry trenching. And then lastly, there are other methods that don't fall into either slurry trenching or in situ mixing, such as sheet piles, the vibrating beam cutoff wall, secant piles. So we'll go over these methods so we have a clear understanding of what your choices might be in remediating a site and why one method might be advantageous to another. All right, so by far the most common method is continuous slurry trenching, certainly the most economical. And again, we have two types of those. We have two-phase and single-phase that we'll see on the next slide. But the first of the two-phase methods, which really illustrates slurry trenching, is the soil bentonite slurry trench cutoff wall or vertical barrier. And in this case, it's two phases because the excavation is completed under a head of bentonite water slurry. And the sole purpose of the slurry is to maintain trench stability. Once the trench is excavated, or in reality, a portion of the trench, the slurry is replaced with a backfill, which is a mixture of soil and bentonite. Normally soil bentonite via slurry, and then if additional dry bentonite is needed, that's added. So you have this homogeneous blend of excavated soils, slurry, and bentonite, which gives you essentially the workability of high slump concrete. So we can see here in the upper right, if I can get the laser pointer working, here we go. Excavation is proceeding with a backhoe. Turns out this trench is too deep for the backhoe. That backhoe could only reach about 50 feet. The trench was 70 some feet. The rest of the trench is being dug with a clamshell. The soil is being tossed over here on the side, and a bulldozer is blending this whole process together. And up in this corner off the slide, the backfill is occurring. If I can get this to play, I would. Maybe I have to go back to pointer. There we go. You'll see a backhoe moving, or bulldozer basically moving backwards. The material has all been blended and it's being pushed into the trench, and it has, it's really a semi-viscous liquid or a semi-solid, and it flows down the trench, and backfill is placed on backfill, and I'll play that one more time, and it displaces the slurry. So on this particular photo, backfill is occurring along here, and you can see all the placed backfill, and excavation is proceeding off to the left. So that's essentially the two-phase method: excavation with a slurry and backfill with a blended material. And if you wonder why that works, typically the permeability is in zones. You might have zones of sand and gravel interbedded with zones of clay. And by digging it all up and homogenizing it, you get this well-graded blend that has a low hydraulic conductivity. The second method of continuous slurry trenching is a modification of the first that came along some years later. And that's where a site needs something more in terms of shear strength than this backfill. And in that case, cement is added to it, and the mixture looks the same and the process goes the same, except the Portland cement allows it to harden in place. And the last technique is the biopolymer slurry trench, which also came along much later than conventional slurry trenching. And that's where the excavation is done with a biopolymer slurry. And that biopolymer slurry is biodegradable. Once the trench is excavated with slurry, instead of backfilling with something of a low permeability, one backfills with gravel to make a drain, or with some reactive material to build a permeable reactive barrier. So biopolymer slurry trenches end up being hydraulic barriers via pumping, but they have a high permeability rather than a low permeability. Okay. In addition to continuous slurry trenching, actually there's the other is a one phase rather than two phase, where the trenching occurs with a slurry that has a binder in it. The cement CB is the oldest form, cement, bentonite, and water, where the cement is a Portland cement. One simply excavates under the slurry and goes away, and when you come back, the slurry is hardened in place and forms a low permeability barrier. Turns out that cement alone, you could probably guarantee yourself hydraulic conductivity at 10 to the minus fifth centimeters per second, but any lower than that is difficult to achieve. Sort of after this technique was established, research in Europe showed that if, instead of all Portland cement, you replace Portland cement with slag cement. In the US, we call this slag cement CB. In Europe, they just call it CB because they all have slag in them, that you can get a much lower permeability, and by 2 orders of magnitude. But it's the same thing. It's a one-phase method. You excavate under the head of a slurry that's made of slag cement, Portland cement, and bentonite water slurry, and it hardens in place. And here's a picture of a slurry wall. It was excavated around a coal tar site. The wall is about 6 meters wide, and this blue color is the manganese that's in the slag. In addition to continuous slurry trenching, there's the panel method, and the idea is the same. One excavates, however, in much shorter panels. So this is the shear wall I mentioned. These trenches are going perpendicular to the slope, the embankment slope, and they're adding shear strength to this embankment. If you think of a deep-seated failure surface. So this happens to be a SLAG-CB slurry wall, and it was really to enhance the seismic performance of this embankment as opposed to the static. And the last panel method is probably one many of you have heard the word slurry trench, and what in our terminology we call that a diaphragm wall. And that's where, again, a panel is excavated. This happens to be a hydro mill excavating a panel. But instead of backfilling or having it self-harden, reinforcing cage is put in. It's a two-phase method, and the slurry is replaced with concrete that's tremmied in. And that's really a structural method. It's pretty rare to be used on an environmental site, only where you need both good moment capacity as well as structure. It's extremely common in construction for tunnels, for subway, for deep foundations, for urban areas, but it's not very common in environmental areas. But just to make sure, when someone says slurry wall to you, if they're a structural engineer, they're probably talking about this type of slurry wall. Okay, besides slurry trench methods, we can do in situ methods of mixing. And this one is with a trencher. It's a trench remixing and deep wall method that is a Japanese technology imported some years ago by Keller. And this is a picture at the Herbert Hoover Dike. And basically it's a giant chainsaw that can have a bar, multiple bars, multiple chains, so you can adjust the depth, not as you go, but you can stop and add or subtract sections of chain and bar. And this is a complicated drawing, but I'll simply say that the chain excavates in one direction, in this case left to right, and in doing so, the material comes around the back and it gets blended by the same chain and grout, if you will, bentonite water slurry, or in this case, bentonite water, Portland cement, and slag slurry are added. And then the blended material, you can walk back and forth and blend this. The blended material is a slurry wall hardened in place that's in a mixture of the entire vertical profile. It's an in situ method of in situ mixing with trencher. Here's a good example of it. This is the Herbert Hoover Dike cross section. And you can see there's random fill, there's peat, there's sands, there's layers of limestone with shells, there's sands that go on forever. So this is a hanging wall. And to reduce exit gradients, the wall was designed to go down to a certain depth and blend it along. But the important part of this is a photograph. It's a 360-degree photograph of inside of a core hole. It's unfolded. And what you can see is this homogeneous blend. Here's little spots of peat. It was a big, thick layer up here. Now it's randomly dispersed. Here's some pieces of shell. So this method does a good job. Trenching does a good job at blending the entire vertical profile and creating a homogeneous barrier. There are other manufacturers. This is the DeWind one-pass trencher. Different kind of configuration, different method of deployment. And of course, there are smaller trenchers that are used for 10 and 20 foot deep slurry walls as well. There are additional in situ mixing tools that have been used to build cutoff walls, the oldest of which are vertical axis augers. You put 4 or 5 of them in a row. You do this in panels, but these are mostly mixing blades. Auger down, mix a section, inject your bentonite water slurry or the grout, and you end up with an in situ mixed wall. However, the zone of mixing is fairly limited. It's, you take soil and you move it up or down a few feet. You don't blend an entire vertical profile. Jet grouting, probably a very expensive way to make a wall, but sometimes when there are interferences, one chooses this technique. That is also in situ mixing, but it uses a hydraulic jet to do the mixing. And so the jet both mixes and adds whatever grout you're going to add to it so that it can harden in place as an in situ mixed wall. A little newer along the mixed in situ mixing are a whole series of horizontal axis augers that various manufacturers have made called cutter soil mixer. And you can see this tool mixes, blends up and down. You can inject the grout, but again, it's going to mix over a narrow range. So if you've got an unsuitable zone for the wall, it's not going to blend that homogeneously into the wall like some of the other techniques. And then lastly, when none of those work for you, there are a few other techniques. Sheet piles, of course, have been around a long time for excavation support. And there have been good developments in sealing the interlocks. This is an older project where the interlocks were sealed by putting it in a CB wall. The vibrating beam has been around for a long time. I'll spend just a minute on this so you can see what I see, and that is this is a big I-beam. It's probably 3 feet into the page, and this is the flange that you're looking at. And inside, between the two flanges, there are slurry jets, and this is a vibrating pile driver. So you vibrate this beam into the ground. It makes a hole of a centimeter or 2 wide. And then when you pull it back out of the ground, you fill the hole with a self-hardening grout. It's sometimes called a thin wall method. And it's not very common because of the fact that it is very thin wall. But the beauty of it is you don't bring materials to the ground surface. So this picture was at a highly contaminated site next to the Nassau County bus garage on Long Island, where they really had no other way to control fumes that would have occurred. And so a vibrating beam wall was used to make the cutoff. Then lastly, on occasion where you also need structural support, secant piles are used. They control both the water flow and they can provide structural support. All right, given that overview and acknowledging that CB is by far the most common, or SB is by far the most common method, let's dive a little bit more into SB barrier wall performance. And I'll address 4 aspects of that in this talk. We'll talk about the final cover. We'll talk about stresses within the wall and why that may or may not matter. That will lead to discussion of hydraulic conductivity and then ultimately compatibility. If we're putting these in environmental sites, we want to know whether they're going to be compatible with the contaminants in the subsurface. So all cutoff walls, all SB walls need to have some kind of final cover on them for 2 reasons: to support whatever the design load must be, would be, and to provide desiccation protection. So this first slide is about the design load, or about, yes, design load. And you can see here is some driver thought he could just drive across the uncovered wall. This is a municipal waste landfill. And obviously, we've seen the material flow. That's not going to happen. So the owner of this landfill needed a final road that they could run loaded trash trucks on the open part of the landfill along the axis of the wall. Seems like a big ask for a material that has virtually no unconfined strength, but with a couple of layers of geotextile, compacted fill, and a good road base, that was built. It's been operating fine. You may not need such a Cadillac solution if you're simply going to have some crossings or you're at pickup truck loads for reading piezometers. But in any case, the wall needs to have some protection to support whatever design loads your project has. It also needs protection to prevent desiccation. And I'll start with the top slide. It's a little complicated. The lower x-axis is the number of cycles of wetting and drying. This is a sandy backfill that has 2.7% bentonite in it. And the y-axis is the ratio between the initial hydraulic conductivity and the conductivity at the end of the cycle, the end of the wetting and drying cycle. So if there were no change, the conductivity would be constant. And then each of these 4 curves represent a different suction pressure. All right. In other words, you're going to have a greater suction pressure in the arid west than you would have in a rainy area of, say, the northeast. And what you can see is that this is the control. Well, we do have a little increase just from taking apart the sample, testing, retesting. But when you have high suction pressures, even after 1 cycle of wetting and drying, you start to get a 10-fold increase in hydraulic conductivity. In this case, ultimately leveled off at a 1,000-fold increase in hydraulic conductivity due to this was only after 3 cycles of wetting and drying at these suction pressures. At the lower suction pressures, you have less effect. But if you do not protect the wall from wetting and drying, you will have increases in hydraulic conductivity. And here's an extreme. This was a wall around an ash facility, a CCR facility, coal combustion residue, where they built a wall and it had a permanent water level because it was an active fly ash pond. And below the wall, from in situ testing, it was 10 to the -8. After 7 or 8 years permanently above the wall, the material dried out so much it was 10 to the -3. This was only after 1 year it dropped a little bit on a newer portion of the wall that was built. The wall was built 2 parts. So in any case, the takeaway message is you need to protect the SB wall, has to be covered for your design loads and to prevent desiccation, because desiccation will result in hydraulic conductivity increases. So moving to the state of stress, I'll first define a term that's familiar to many of you, but perhaps not all, and that's the geostatic stress. And I'll simply say that's the weight of all the soil above a point. So we normally think about calculating stresses in the subsurface by taking the weight of all the soil above the point we're interested in. And effective stresses, we'd account for the pore water pressure. Turns out for SB slurry walls, we're putting this soft compressible material in a formation that is inevitably less compressible. And as the material consolidates, it tends to transfer load to the sidewall. And the backfill settlement is resisted by the shear forces along the sidewall. So this is a very old source where this was first postulated, and nobody really had any idea what these stresses were. We did know they were less than theoretical geostatic. And now we'll fast forward to a wall that was built, full-scale wall built for research purposes, where load cells were installed to actually measure the stresses. And here's some reasonably long-term stresses. And now these are effective stresses where the pore water pressure is accounted for. And this is what the geostatic would look like. But because of this load transfer, the actual stresses are lower. And it also turns out, because of this load transfer, there is a rotation of principal stresses. Don't worry about it if you don't know what that means, but now the horizontal stresses are higher than the vertical stresses. So we have the transverse horizontal, we have the longitudinal stress in blue, and actually the lowest stress is the vertical stress. And so at a depth of about 6 meters, we're looking at effective stresses of 15 kilopascals. Now, of course, the deeper you go, the higher these get. But it's important to know that the stresses in SB walls are less than geostatic. And if it matters to you, there are publications available, including this one, that would tell you how to calculate those or estimate those. Does that matter? Well, maybe. On the left, we have some permeability tests on 4 different bentonite contents, mortar sand, base soil, really test some very high effective stresses. And you can see that for the most part, unless the bentonite content gets really high, that's 5%, and most encounter, it really, the hydraulic conductivity is largely stress independent. There's a lot of grain-to-grain contact. Adding additional stresses does not cause much consolidation. The more bentonite you have, the more consolidation you're going to occur. So low fines, base soils, probably not a problem. On the other hand, this is data from a real site in Birdsboro, Pennsylvania, where it was a high bentonite content mix and it had a high clay content. I did not design the mix. But we can see here that there was a 2-order magnitude decrease in hydraulic conductivity as the stresses went from 10 kilopascals to over 100. We can also see that the variability, these are error bars, the variability at low stresses is greater than at high stresses. In other words, you can consolidate out the variability. So if you have this kind of soil, you want to make sure you're testing your hydraulic conductivity in the range of stresses that you expect in the field. So the hydraulic conductivity may be stress dependent, and that will depend upon the base soils used. So the last issue with soil bentonite is compatibility. And compatibility is basically whether or not the material will change in hydraulic conductivity. And a lot of people worry about organic contaminants. And here we have, just as an example, organic aniline, which has a solubility limit of 30,000 parts per million. And after some permeation with water, where there's some particle rearrangement and decrease in hydraulic conductivity, the aniline replaced the water as the seepage permeant, and there's really no impact of the aniline. That's dissolved phase organic fluid. If you take that same aniline, which cannot exist at 40 or 50,000 or any other concentration above 30, because that's its soluble limit, at that point it becomes a non-aqueous phase liquid, NAPL. That non-aqueous phase liquid, when that replaced the water, that had a pretty dramatic effect on the hydraulic conductivity, and fairly quickly. Here's 1 pore volume. You start to see the effect even after half a pore volume of flow. It actually does level off. It doesn't go on forever. It levels off to the hydraulic conductivity of the base soil, which again goes back to the importance of the base soil. So the takeaways we can have about organics is that really we only have to worry about non-aqueous phase liquids, floating products, dense non-aqueous phase. They're the only ones that really affect SP compatibility, and that has to do with the dielectric constant of these materials. In any case, you want to run site-specific compatibility tests. If you have no NAPL on the site, you still run it with the groundwater with the dissolved phase. If you have NAPL that's sampleable, you can go to a well, get significant volume of non-aqueous phase liquid to run in a lab, run a lab-specific compatibility test and see if it has an impact. And lastly, again, the magnitude of the impact depends upon the base soil grain size distribution. And we'll see about this in a minute as well. Inorganics are probably the more prevalent contaminant at a lot of the sites. This is the table from WyoBen, which I got from Paul. And WyoBen sort of has kind of a rule of thumb. If you're worried about calcium, don't worry unless it's at least 500, magnesium 150. And it has to do really with the ion valence. Our bentonite is sodium bentonite +1. If you have a cation exchange of sodium +1 to something like calcium +2, the bentonite will shrink, and then the shrinking of the bentonite may cause an increase in permeability. It also depends on the concentration, and it'll depend again on the base soil. So here's another set of data that puts a little nuance on these up or down yes or no tests. And you can see this is calcium chloride at 50, 200, 500, and 1,000 these are in moles, but they were in milligrams per liter. But nonetheless, the point is you can see that as you permeate, this is first tailwater, and then the calcium chloride is added. And this is adding the calcium chloride from the beginning. And at the end of the day, it doesn't matter whether you start with water and switch out the fluid or whether you start with the contaminated fluid. But even at 50, you do get an increase in a long-term test. Now, how long does it take in the field to have 5 pore volumes of flow? That might be 50 years. So this is a time scale as pore volumes of flow, and under field gradients, it may take many, many years for this to occur. And at the end, the concentration is somewhat irrelevant because at the end, you're going to provide enough calcium to have a cation exchange with the sodium until you get a new equilibrium. It just occurs more quickly with a higher concentration. And that's why in a table like this, you see it more quickly. So it becomes more of a trigger in a short-term test. So impact of organics, concentration dependent to some extent, short-term, but not necessarily in the long term. Depends on the valence, the concentration of the soil. Again, run a site-specific compatibility test. The behavior is understandable in terms of colloidal chemistry. So I keep talking about the base soil, and I wanted to draw you a picture. If you have a well-graded material, you have fine gravels and smaller gravels and coarse sand and medium sand and silt, which is inert, and low permeability clay. And if you can progressively make a grain size distribution for your backfill, you're really only relying on the bentonite to plug the smallest of the voids. And if it weren't there, you think of a glacial till. That's got a low hydraulic conductivity in and of itself. So really for low permeability, low compressibility, and best compatibility, you want a well-graded backfill, you want some natural fines, and you want to use as little bentonite in your design as possible. So summary of SB design: hydraulic conductivity may be stress dependent, but it's certainly the stress dependent increases with increasing fines content. Often just mixing bentonite water slurry with base soils, when you do the phase diagram on that, that adds about 1% bentonite. That's often adequate to get 10 to the minus 7 centimeters per second or less. So many times you don't need dry bentonite for your mixture. And you can, of course, decrease the hydraulic conductivity by simply adding more bentonite. And for best compatibility, since the bentonite swelling is reversible, you want to use the least amount of bentonite possible. So let's talk in our remaining few slides in a few minutes about the slag or the CB walls. We'll talk about the benefits of slag, how that affects hydraulic conductivity, and then we'll talk about compatibility of CB. So here is a simple chart. There are a lot with a lot more complication, but I think this really illustrates. This came from a paper that Stephen Jeffries published, and he did the work in England quite a while before this particular curve was published. But in essence, what he's showing you is if you take a CB mix, let's say you use 20% cement in your mix, 20% binder, and you use 20% binder, you're in the 10 to the minus 5th, 10 to the minus 6th range for straight Portland cement. And even if you go up to as much as 60%, and this is the amount of slag in the binder. So if we think about this axis, this would be 100%. Oh, shouldn't have touched that. This will be 100% slag. This will be 0 slag. This will be 100% Portland. This will be 0 Portland. So clearly, somewhere in the range of 70 to 80%, he found that there's a 2 order of magnitude drop in hydraulic conductivity. So if you have a mixture of CB that's going to be 20-25% binder or 10 to 20% binder, and you use 10 to 25% Portland, you'll be using 75 to 90% slag, and that's going to give you the lowest hydraulic conductivity. And that's really where the industry has evolved to at the present. And that's whether you use it as CB and self-hardening, or whether you use that as an additive for in situ mixing. The mixture would be the same. That is, you want to be using 75 to 90% granulated ground blast furnace slag and only 10 to 25% Portland cement if you want to achieve these low hydraulic conductivities less than 10 to the minus 7th centimeters per second. There's a hitch to this, however. We, all of us have probably civil engineers have taken a concrete course, and we think of 28-day strengths. And with Portland cement, it hydrates fairly quickly. With slag in it, the curing times can be much longer. These are samples that cured over the period of a year, and this is hydraulic conductivity. And you can see that and this is meters per second. So this would be a 10 to the minus 6 centimeters per second. And look how high these hydraulic conductivities are at only 1 month. But a year later, they've dropped down tremendously. So in our field quality control and our design, we have to wrestle with this issue, knowing that the hydraulic conductivity, all 3 of these mixes at 12 months dropped below our magic 10 to the minus 7 centimeters per second, yet only 2 of them after 6 months. And of course, the lowest, the 90% slag didn't drop down low enough at all. But in these 70, 80, 90% range, we can get the hydraulic conductivity. We're just not going to see it in 30 days. And in case you need strength, as you put the slag in, you also get the best strength. So you get best hydraulic conductivity and best strength by using slag in the mix. And you can see here's a sample of the material, and that purple is manganese that comes apart as part of the slag. So we know we can get hydraulic conductivity. Where does SLAG-CB fit into our scale of compatibility? And here's some aniline. 12-month test, no change. Here's ethanol, no change. Here's immersion test with no confinement. Again, a hydrated SLAG-CB is a fantastic material for compatibility. And here's the reason why. Bentonite, which is a construction expedient, is actually, you can study this more at your leisure, but the bentonite essentially disappears. Once this hydrates, there's virtually no evidence of the bentonite, so all those issues about bentonite shrinking, swelling, causing permeability changes, those are irrelevant because now you have after curing, you have a hydrated concrete-like product. And so the optimum design for SLAG-CB is some mixture of 15 to 20% binder, cementitious material with about 70 to 75% slag. SLAG-CB is far more compatible with organics than SB. Where you run into an issue with SLAG-CB, just like you would with cast-in-place concrete, is if you have high sulfates in the groundwater, and particularly under unconfined tests like the immersion tests. Confined tests tend to show better compatibility, but you do have to worry about sulfates in the groundwater if you're using a CB mixture. And finally, the bentonite's a construction expedient. It's not relevant to later considerations of compatibility. All right, so overall, what I tried to cover today in 45 minutes is that the developments in construction have increased both the range of materials, the depths, our ability to build a quality wall, and a lot of that credit goes to the contractors and their willingness to try new equipment and to develop equipment. Our understanding of stresses, compatibility have improved, a lot of research, and a lot of practical site-specific tests. But we now can pretty confidently and effectively design vertical barriers for environmental containment. The developments in mixed design, basically using granulated ground blast furnace slag, have provided additional slurry options that weren't really used when I started my career. It was strictly Portland cement and bentonite. Now it's widely used, and you have a lot more options for both harden in place and for in situ mixed walls. There is a considerable body of experience in both the contracting side and the design side of vertical barriers, and that experience can be drawn upon to effectively design and build vertical barriers. And then vertical barriers as a component of site remediation can achieve long-term protection of the public health and the environment in a more sustainable manner than active remediation systems, which may be attempting to get every molecule out of the ground. So with that, I think I will say thank you for your attention, and I'm now available to answer questions.
Thank you, Jeff. That was a really informative presentation. I know I learned a lot, and I expect everyone in the audience learned at least something new. If there's any questions, you can raise your hand and we'll call on you, or you can enter your question into the chat. The link to the forms to PH credit, if you'd like to receive one, has been posted in the chat a couple times throughout the webinar. If you have any issues accessing that form, you can contact us and we'll get it to you. And if you missed any of the questions or content that would help you answer them if you don't know it, a recording of this webinar will be posted on YouTube in the next few days. First question from, I'm going to butcher your last name, I apologize, Ruben. I'm going to call you Ruben M. Do you have an experience with thermosiphons?
Say again?
Do you have any experience with thermosiphons?
Thermosiphons? No, I do not.
Yeah, I guess they clarified thermosiphons as a form of vertical barrier.
No, this sounds like an active technique. I'm not even familiar with the term.
Next question from Scott Hartzell. Can you touch on the relative costs of soil bentonite slurry versus soil bentonite soil mix and soil cement bentonite slurry wall designs?
Yes, and I'm working from some work I've done recently, not yet published. If you think about soil bentonite cost being X for a given project, so many dollars per square foot, CB walls are often 2 to 3 times X, so they're twice as expensive. Collection trenches can be 3 to 6 times X. In situ mixing techniques, trenchers can be cheaper sometimes they can be more. Things like sheet piling are going to be 3 to 6 times more expensive than SB. Diaphragm walls are 5 to 20 times more expensive. So SB tends to be the cheaper, other than the only thing that can really compete with it is the trencher. On the right job, a trencher can be cheaper than conventional slurry trenching. But sometimes conventional SB slurry trenching is just not suitable for the site.
Okay, thank you. We have a Molly Foster. You have your hand raised. You can go ahead and unmute yourself and ask your question.
Yes, we had a question for you. So I am with the Parsons structural team, and we are currently using slurry walls or proposing to use slurry walls in order to excavate and do our dewatering process in order to construct CIP walls in front of them. So our structural walls will go in front of the slurry walls eventually. In order to construct these walls, or in order to get the utilities through our walls, we will have to have pipes passing through our walls, roughly of the diameter of about 3 feet. So the CIP wall that sits in front of the slurry wall is going to be approximately 5 to 7 feet thick. And we're proposing to place some kind of block out during the construction of the CIP wall in order to later pass the pipe through. How do you guys approach this in terms of slurry wall construction? Is there a certain method that you use for the placement of these pipes in the future? Do you use a block out of some kind, such as styrofoam, or is there another methodology that you would recommend?
Well, certainly blockouts when you do a diaphragm wall, they anytime you need a penetration of the wall, you can do that with the styrofoam blockout. I guess I don't have a good visualization of the entire project. It sounds like you're using the cutoff wall first to dewater and maintain the control. So I guess I would suggest maybe you contact me offline and maybe send me a sketch, and I can do a better job of answering the question for you.
We'll go ahead and do that. Thank you so much.
Okay, sorry.
Next question from the chat is from Praveen Kumar. Other than the application to environmental protection, can these be used in deep foundation construction?
Yeah, the 2 most common applications in deep foundation construction are for dewatering excavations. That is, if you have room for an open cut. My very first project was an SB wall adjacent to Lake Michigan and adjacent to a water channel where we needed to build a building with foundation 60 feet down. And you can put the wall in and then just a little bit of pumping to, if you will, drain the bathtub, and then they'll maintain the groundwater control and gradients. So they are used a lot for dewatering for excavations. If you want to combine structural support with them, that's where you get into some of the other techniques, like using a diaphragm wall or using for instance, the augers, the multiple auger in situ mix wall. You can mix, instead of just slurry, you can mix cement with those, and you can drop I-beams in. So you can control both groundwater, and then you can have sufficient modulus to either have a cantilever wall, or if it doesn't have adequate modulus, you can do tiebacks. So most of these techniques, other than just plain, well, most of these techniques are adapted to traditional civil engineering construction in the subsurface.
There was actually a follow-up question from Praveen about that. Are these barriers more economical than sheet piles?
Usually, sheet piles are an expensive technique. You'll see them more widely used in really narrow urban areas. You have to bury a pipe down a street. You don't want to open up a big hole, and you can't make a mess. But where there's room to work, most of these techniques are more economical than steel sheet piles.
Okay, next question is from Karina Zuber. You mentioned that SLAG-CB was used in Europe. Is there a reason why the US mostly uses SB?
I think it's a matter of there's actually a philosophical book about this having to do with, how do you control satellites, and the Russians do one thing and we do something else. And it's a matter of the history and the experience of both the designers and the contractors, and the discovery that slag worked to help lower the hydraulic conductivity was made early enough in Europe that they started using that, and they gained experience in design with it. We started a little ahead of the game cleaning up hazardous waste sites. Superfund passed in 1980, so we were a bit ahead of the game, and SB walls were an available technique then. And so we morphed them from groundwater control to environmental containment barriers, and we built a large body of experience with designers and contractors in SB. And it's only been really in the last 10 years that the experience with companies like Keller that are owned by a European company that are doing some more cross-fertilization, that we're seeing the more common use of SLAG-CB.
If there's any more questions, feel free to enter it in the chat, or you can raise your hand and we'll call on you to answer it live. I guess if we can go to the next slide in the meantime.
Can do.
So our next webinar will be on March 8th, presented by Kristen Brooks on overcoming unique challenges associated with MGP impacted sediment during design and construction. So that'll be posted on our LinkedIn and website in the next month or so. I don't see any questions coming in. Oh, there's one more from Paul Boyajian. Why is the problem of adding lots of bentonite to reduce the hydraulic conductivity? Oh, sorry. Why is it a problem to add lots of bentonite to reduce the hydraulic conductivity of the SB wall even further?
The beauty of bentonite, and the reason civil engineers use it all the time, is that it is a high swelling material. And the downside of bentonite is that swelling is reversible. So if you add a lot of bentonite, you can greatly reduce the hydraulic conductivity. And if you're doing clean groundwater dewatering, that's probably fine. But if you have contaminants, as we've seen, both inorganic and organic, that can cause the bentonite to shrink again, then that hydraulic conductivity can increase back up again, really ultimately to the hydraulic conductivity of the base soil. So the point I was hopefully trying to make is that it's better, and there have been sites where we've done this, where we just bring in additional fill material to make the backfill, because with a good homogeneous blend of backfill consisting of gravel, sand, silts, and low activity clays, you can achieve both low hydraulic conductivity and good resistance, good compatibility, resistance to the contaminants.
Okay, well, thank you, Dr. Evans. I really appreciate you having you on today and giving a great webinar. Thank you to everybody who joined us today, and we hope to see you again in March.